course. The only thing that was remaining was distribution. I introduced what is PMF, what is PDF, but we did not really discuss about any specific distribution, and we will not discuss about many distribution, but I will discuss about one distribution, because that we will be using repeatedly throughout this course, and that is the Gaussian distribution. So, we will be talking about univariate Gaussian today, the multivariate Gaussian today, and then we will talk about the transformation of distribution, and after that we will start with the main thing. Okay. So, these are the three things that I will talk about. Remember last class, at last I discussed about KL divergence. That will come maybe around lecture 18, 19 or maybe. So, the concept of KL divergence will not come for the initial part of the course. We will only get it when we go to approximate inference, which is lecture 15, 16, something like that. So, with that background, let us start. So, we discussed about PDF and PMF. PDF is probability density function, and probability density function is for continuous random variable, right. Gaussian distribution that we are going to discuss today is for continuous random variable, right. So, we are going to talk about Gaussian random variable. Okay. And the first thing that you will need to define a random variable is its PDF, but a probability density function, and the PDF for Gaussian random variable is represented in this form: 1 by sigma root 2 pi exponential of minus half x minus mu by sigma whole square. Okay. Okay. So, this is the PDF of Gaussian random variable. What is x here? X is my random variable. So, x here is the random variable, that is what you see in the left hand side. Now, along with x you see two more things. One is the mu, which is the mean, and other is the sigma, which is the standard deviation, and these two, which are mean and standard deviation, or mean and variance I can call it, are the parameters of a Gaussian distribution. So, mu and sigma or mu and sigma square are known as the parameters of a Gaussian distribution, which means that if you know mu and sigma, you know the distribution. So, those are the things that you need to know. Without knowing mu and sigma, your distribution is not completely defined. Okay. And how do you write it? So, the common notation is that you use calligraphic n, because the other name of Gaussian is normal. So, that is why n, and then x is the random variable, and then you write like conditional, it is conditioned on the parameter value which are deterministic, mu and sigma square. This is how you represent the Gaussian distribution. So, wherever you see something written like that, you should know that this is the Gaussian random variable that is being talked about, where this is my mean, this is my variance, and these two together are the parameter. Okay. So, mean and variance are the parameter of Gaussian random variable. Okay. Now, this is a very important distribution, because it has certain properties which allows us to do things in an analytical way. For most of the distribution, as we will see throughout this course, you will not get closed form solution, you will not be able to do things in an analytical manner, that will not be possible. For Gaussian, actually it is possible, and that is why it is the most popular distribution that is there. Whenever you don't know anything, we assume it to be Gaussian. I mean, that is what we are doing, right? So, the other way of writing Gaussian distribution is again, if you assume x to be a sample drawn from Gaussian distribution, this kind of notation is also there, that is commonly followed. So, in this case, it means that x is a sample drawn from the Gaussian distribution with mean mu and variance sigma square. So, these are just notations that are or representation for ease of communication. Okay. These are just representation. Okay. Now, mean of Gaussian distribution we already discussed is mu, that is the parameter. Variance is sigma square. So, variance of Gaussian is sigma square, okay? And this is a distribution that is symmetric about the mean. So, if you take the mean, the left hand side and the right hand side will become mirror image. So, it is a symmetric distribution. Gaussian distribution is symmetric, okay, which means probability that x will take value less than mean is equal to 0.5 and probability x will take value greater than mean is also equal to 0.5 and it is symmetric. Not only that, I mean that is one of the conditions that you get because of this symmetry. Okay. Also, mode. What is mode? I did not discuss it. So, what is mode of a distribution? Highest frequency. So, the most probable point, you can think of it like that, the point that has the highest, most probable point, the peak, yes. So, mode of Gaussian is also equal to mu, okay. That means, it peaks at mu and then it symmetrically goes down as you go away from the mean, okay. So, how does it look like? So, it looks something like this, where this you see here is your mu, which is your mean, which is your mode both, and the left hand side and the right hand side are supposed to be symmetric. If it does not look symmetric, it is because of my drawing, it is supposed to be symmetric, okay. And yeah, and theoretically the value x, which is a random variable, can vary from minus infinite to infinite. So, x can take any value in theory from minus infinite to infinite. So, x can take any value from minus infinite to infinite, okay, any value in theory. But in practice, you will realize that most of the time, because we cannot work with infinite, we do not like to work with infinite, most of the time we will restrict ourselves to mu minus 3 sigma to mu plus 3 sigma, and there is a reason for that. The probability that the variable x, assuming it is following Gaussian distribution, will reside between this range of mu minus 3 sigma to mu plus 3 sigma is 99.81% or something like that, which is a very high probability. So, almost with very high probability your variable will be between x mu minus 3 sigma to mu plus 3 sigma. So, for practical purpose, we consider x belongs to mu minus 3 sigma and mu plus 3 sigma. And we can consider that because, as I said, if you compute the probability, integrate between this range, you will find that it is quite high. So, for probability we can do so because probability mu minus 3 sigma is less than equal to x less than equal to mu plus 3 sigma is approximately equal to 0.9981. I mean, you should check the number, but 0.998 is definitely there, okay, which is quite high, as you can see, right, almost equal to 1. And so, in practical scenario you can do that. But if you are suppose working with a important system such as let us say nuclear reactor, then probably you should take mu minus, I do not know, 10 sigma to mu minus plus 10 sigma, because even this much tolerance is not allowable in such cases. In that cases you will probably want accuracy up to 10 to the power minus 20 or something like that. In that case you can adjust that 3 number accordingly, okay. But for all most of the problems we solve, this range is reasonable. There is another number which is very important, which is 1.96, okay, or we take it too often. So, probability mu minus 1.96 sigma mu plus 1.96 sigma is equal to 0.95, okay. So, in practice we do not use 1.96, we use 2. So, we say 2 sigma bound, and that is known as the 95% confidence interval. So, 95, where does this number come from? There is no reason, I mean just 95% I want to be accurate or something like that. If you want to be more accurate, you have to change that number, but 95% confidence interval is a very common quantity among statisticians, among machine learning researchers, among anyone working with statistics. So, 95 is considered to be a like 5% tolerance is allowed, right. In that case, this is the number for you. But in practice, remember, we generally work with 2, not 1.96, because it is easy to calculate, okay. So, yeah, but this is about univariate. What we will be needing in this course is not univariate, but we will require in this course throughout, at least for 90% of the course, is multivariate. So, let us now go to multivariate and try to generalize this Gaussian to multivariate case, okay. So, we like to generalize it. So, generalizing to multivariate case. First of all, how will the PDF look like, right? This is now equal to, what was there? 1 by sigma root 2 pi. So, root 2 pi will be there, but it will be there if there are k variables, it should be root 2 pi to the power k or something like that. So, it will you will get actually 2 pi to the power minus k by 2, where I am assuming that x is a multivariate and it has k states, okay. So, it is a k dimensional variable, it is a vector where there are k entries, okay. And then there was sigma square, which is the 1 by sigma actually. So, which was the, so square root of sigma square, you can think of it like that. Sigma square is your variance. For multivariate case, only variance is not enough, you will also need the covariance. So, you will have the covariance matrix, and so you will have the covariance matrix, and it was sigma, not sigma square. Covariance corresponds to variance, so it should be minus half, okay. Yes.
How did we go minus half?
It was 1 by sigma square, square root. So, square root, because of that minus half, 1 because it is in the denominator, and sigma square becomes this, and it has to be determinant because it has to be scalar, okay. And then you had exponential, and inside the exponential, what was the quantity that was there? Minus half was there, so it should stay. And then you had x minus mu by sigma square whole square, right. Now square does not hold any meaning when it is vector. It has to be vector multiplication. So square is generally x square is generally x transpose x. So that thing should come now. So x minus mu transpose, and then sigma square was there. So that will become and then x minus mu. Sigma inverse. Sigma inverse. Okay, because it was 1 by x minus mu by sigma square. Okay, where this is known as my covariance matrix. Covariance matrix, and mu is known as my mean vector. Mu is known as my mean vector. So mu, what will be the dimension of mu? Remember, I assumed x to be k dimensional. So mu will also be k dimensional. So it will be of dimension k. Okay, because my x is k dimensional, and your sigma will be covariance. So if there is k, it will always be k cross k. K. Okay. I don't think there is anything else to be defined, and this is represented using the same exact notation as the univariate case. So calligraphy again. So this is, I mean, this by this I means multivariate Gaussian distribution. Okay, is represented as Gaussian, let us say x, which is a vector now, given mu comma sigma. Okay. And remember, sigma is the covariance matrix. Inverse of sigma is known as the precision matrix, at least in Gaussian case, and you will realize that, or you will see that in most or many books we often work with the precision instead of the covariance, which is nothing but inverse of covariance. Why? Because it makes our life easier, calculations are simple, no other reason. If you want, you can work with either, the results will not change. It just to make our calculations easier, because this inversion and all those things you do not want. Okay. Now sigma is a covariance matrix and it has certain properties. The first thing is that it is symmetric. Okay. Its eigenvalues will be real. Okay. Because it is symmetric, so positive semi definite, assuming some 0 values. Okay. But those properties we will need later, not now. But one important property of this Gaussian distribution is that if we find out the marginal distribution. Now what is marginal distribution? Someone? We covered it last time.
Sum of all the.
Not all. I mean, if you integrate out some of the variables, that is known as the multivariable. Like probability of A is equal to integration of probability A comma B dB. So then that is the marginal distribution. That is the sum law of probability. Okay. So marginal distribution will also be Gaussian. If your joint distribution, this is a joint distribution, right? Because you have k variables. So if the joint distribution is Gaussian, your marginal distribution will also be Gaussian. And not only that, your conditional distribution will also be Gaussian.
So
Okay.
in the Gaussian distribution of transpose will come up the others vector.
That will become in the, when you calculate covariance, because it has to be a scalar. So if you have defined vector like this, transpose, then only you will get a.
We are taking x as column vector.
X is a column vector, right? Because remember, PDF is a scalar, the output of that function PDF is a scalar. So where the transpose will be depends, you have to define, depends on how you have defined your vector. If your vector is like that, then the transpose would come at the end, because only then you will get a scalar. But if your vector is like this, then it will be like this. Okay. And same thing will hold when you try to find, let us say, covariance. You have measurements, right? In that case, it becomes x transpose, because only then you will get, it is the outer product, only then you will get a matrix, otherwise you will end up getting a scalar. So, that part you can easily adjust based on by knowing what is the output you are expecting. Okay. So, the point I was trying to make is that if joint distribution is Gaussian, then marginal distribution and conditional distribution are also Gaussian. And this is the property that allows us to find closed form solutions when working with Gaussian distribution. And this is the reason we often work with or assume things to be Gaussian when we do not know things, because leave. Okay. Okay. So, class होने से भी 20 minutes is too much. Your class ends at 9:30. Okay. So, go and tell that. Okay. आ जाओ from next day. Okay. So, yeah. So, yeah, if joint distribution is Gaussian, then marginal distribution and conditional distributions are also Gaussian. So, how do you write it? So, the probability, let us say A comma B is Gaussian with mu comma covariance, okay, where mu looks like mu A, mu B, and the covariance looks like covariance of AA, covariance of AB, covariance of BA, right. So, then I will not give you the formula, but I will tell you that probability of A will also be Gaussian without giving you the value, and not only that, probability of A given B will also be Gaussian, probability of B given A will also be Gaussian. Okay. Repeat. Will also be Gaussian, obviously. Correct. Probability of B will also be Gaussian. Okay. And remember, here A and B are vectors I have considered. So, it is not like A and B are scalar, and that is why I have written it in this form. Okay. So, A and B are like you divide x k into 1 to j and j plus 1 to k. So, both of those are becoming vector. So, A and B are also vectors. So, from k variables you take a subset of that and the remaining, and that becomes A and B. Okay. So, A and B here are not scalars, and that this property holds for any size of subset. So, that means probability of x1 given x2 to xk is also Gaussian, probability of x1 to xk minus 1 given xk is also Gaussian. Probability of x1 is also Gaussian, probability of x1 to xk is also xk minus 1 is also Gaussian, where k and k minus 1 all of these things can vary. So, basically whatever you do you will end up getting a Gaussian. So, that this means, as I said, if probability of x1 to xk, this is your x actually, is Gaussian without writing mean and sigma, then probability of x1 will be equal to Gaussian, probability of x1 comma x2 will be Gaussian, probability of x1 xk minus 1 will be Gaussian. So, basically any subset you take, anything you marginalize, you will always end up getting Gaussian. Same property holds for the conditional also. x1 given x2 is Gaussian and x1 given x2 to xk is Gaussian, whatever you do, it is always Gaussian. Okay? And that is the property that will be really useful to find out closed form solutions when we go into Bayesian inference, not today, but when we start talking about linear regression. Okay. So, this is the reason it is so popular. And I will stop here on the probability distribution part, the Gaussian part, but you should definitely read about some of the distributions I mentioned last time, starting from Bernoulli, binomial, beta, multinomial, gamma, inverse gamma, there is wizard distribution also. So, these are some of the distributions you should definitely read about, because we will be needing them going forward, and I will introduce them when we need it, the PDF at least, as and when I need it basically I will introduce them, but I will not introduce them now. There is also student state distribution, that is something also we will need. Okay. So, we will need all of this distribution. So, please read about them. I will introduce them as and when those comes up during some derivation in this course, but we will not discuss it now. Okay. Okay. So, the next thing we want to talk about is transformation of distribution. Okay. This again will not be needed now, this will be needed when we go into invertible neural network, which is towards the end of the course, but this has very useful application throughout statistical inference, statistical computing and all of those things, but we will not see that in this course until and unless we go into invertible neural network. Okay. So, the next thing is transformation of distribution. Okay. So, suppose I have x which is a sample from some distribution, and let us say x is a sample from f x x, where f x x is some PDF. Okay. So, all the properties of PDF holds for f x x. I have another variable y coming from another distribution, okay, and all the properties of PDF holds on f y y, right. I know one more thing, which is the relation between small x and small y. So, I know how these two samples are related, and let us say I know that y is equal to g of x, where g is some known but non-linear type of function. Okay. So, g is known but non-linear function. Okay. So, now what I want is to find out the relation between f x x and f y y. Understood what I want? I want to find the relation between the two PDFs. So, the objective is to find the relation between the two PDFs from which x and y are generated. So, the objective is how the two PDFs are related. Okay. That is what we want to find out. Now, do you think if I just let us say do g of f x x, I will get f y y? If I just take that g function, which is a nonlinear function known to me, and if I apply it over this f y y, which is the f x x, which is the PDF of x, will I get f y y? The answer is no, it does not work like that. And the reason is there are certain properties PDF should satisfy, and that will not be satisfied if you do that. Okay. For example, it will not integrate to 1 if you do that. Okay. So, that does not, it does not work like that. So, how to do that? So, we have to use the property of PDF, and the property of PDF is that it should integrate to 1, that is one of the property. Not only that, any transformation you are doing, so take a more small slice and let us say I am transforming that mass is supposed to be preserved. So, what I mean is that suppose I have a PDF, let us say this, and this is my PDF of let us say f x x. Okay. I have another PDF, something like this, okay, and let us say this is my PDF of f y, y. And I am interested in this transformation or this transformation, one of this, right. This is what I am interested in, and the property is that both of these should integrate to 1, that is property number 1. So, number 1 is integration of f x x dx should be equal to integration of f y y dy, and both of this should be equal to 1. I am assuming I am integrating from minus infinite to infinite. That is the assumption. I am not showing it, but that is to be noted. The second property is that in PDF or probability distribution, it is mass conserving. What does it mean? It means that suppose I take this mass, a small strip here, okay, and let us say this strip, if I transform to this, I will get, let us say, something like this. Okay. The area under the curve on the left hand side and the right hand side is supposed to be conserved. It cannot change. That is the property of PDF. So, it cannot happen that something enlarges, other thing reduces and the sum is 1. That is not a property of PDF. The property of PDF is it is mass conserving. So, if you take a small area, that when the transformed, the area is conserved. So, and this is a property that we will be using. So, let us say this probability mass is m1, this is m2. So, the property number 2 is m1 is equal to m2. Okay. So, this is getting transformed here, let us say. Okay.
What does this mass represent?
Probability.
What is the length and breadth?
So, that I have to, I will decide, right, what is the size.
So, we are taking arbitrary?
Arbitrary, because I have to prove something, so I have to take arbitrary. So, I will take dx and some height, right. So, dx and dy. Okay. So, yeah. So, let us say this length is, because I want to prove it arbitrarily. So, let us say this is my dx and this is my dy. So, I am taking differential length. Okay. So, it will be dx times fxx. So, at a distance x, if you take dx, so you know the area is dx times fxx, the left hand area. The right hand area is dy times fyy. So, this will result in fxx dx is equal to fyy dy. Okay. Understood? And now, we can write that f x x is equal to f y y dy by dx, and I will put an absolute sign here. Why? It should have been put before also, in the last step also you can put, but I will put it here. Any idea why? Because the left hand side is probability density function, which is supposed to be greater than or equal to 0. This ratio can be negative because y and x has a y is equal to gx I assumed. So, that derivative at a point can be negative, right. So, this ensures that your probability mass is positive, that property is suggested. So, ideally you can also write mod of dx and mod of dy in the previous line itself, and that works. Okay. And now, what is y equal to? G of x. So, fxx is equal to fy g of x, and then what is dy by dx? G that is x. So, that is the transformation law for univariate case. Okay. For univariate case, this is the transformation law. Now, you tell me for multivariate what change do you expect? For multivariate case, what change do you expect? y will become y1, y2, yk. X will become the vector x1, x2, xk or something like that. So then this derivative will have no meaning. It has to be partial derivative, del y, del x. And then you were talking about area, determinant, mod. Okay. So,
Sir, I didn't get the theory for taking strips, like why we are taking.
okay. So we are taking this strip because the property is that when you are transforming, right, the whole distribution is getting transformed. Previously the integration was 1, after that the integration is supposed to be 1. The second property of transformation or the second property of probability distribution is that even if you do not integrate the total thing, you take a small strip and integrate it and then transform that. Even in that case that area should not change, which means if probability of x2 less than equal to x less than equal to x1 something like that, if it x2 becomes y2, x1 becomes y, that probability is supposed to be same. So that is why we call it mass conserving. So that means it is not a total mass I am talking about. No matter how small a strip you take, the mass is supposed to be conserved. Mass means probability, you know. So the probability is supposed to be conserved. Okay. So yeah, for multivariate case, fxx will be equal to fy g of x determinant of the Jacobian, which is del y del x. Okay. Del y by del x is known as the Jacobian, which is a matrix. Okay. Any question on this part? This part is clear. This we will not need now, but this is very important to note that it is possible to transform from any distribution to any distribution. So there always exists a one-to-one mapping between distribution. Now whether you can find it or not is a different story. There are serious research that is going on to find this kind of transformation. For example, optimal transport is a huge research area now. So optimal transport is how can you go from one to another, one distribution to another distribution. So this finding out this transformation is not straightforward, and you will realize it because when we solve you will realize that gx is non-invertible. So if I have to now based on this find out fy based on fx, I cannot because I do not know the inversion, and all of this problem will come, but that we will discuss towards the end of this course when we talk about invertible neural network, where we will talk about affine transformation and all those things to actually allow this. Okay. For now, this is the equation, let us say, that we derived that you can use to transform from one distribution to another, given you know y is equal to gx, given you know y is equal to gx. I mean that is to be known, the function g is to be known and the form of fy is to be known, and then you can find the form of fx. Okay. Clear? Okay. Yeah.
I have a doubt in the notation. You said small x is sampled from f capital X bracket small x.
Yeah, yeah.
So what is the, I mean, like that small x is input to f capital X. So how is small x again sampled from?
Correct. Small x is not an input. So think about it. Gaussian distribution let us take, that will actually help you understand. Where is it? Not this one, the simple one. Okay. So now there are two parts you can do. One is you know x and you want to find out the PDF. In that case what will you do? You will take that x, substitute into this equation, mu and sigma you know, you will find out some value in this curve, some value on the curve, right? That is one way. The other thing you will realize that you have to remember that this PDF corresponds to some random variable, and often you will see that you cannot work with the random variable directly, you might have to work with some samples of the random variable. So that comes under the idea of sampling based method, where the idea is I know the distribution, but can I draw samples from the distribution, samples that will represent that. For example, samples, if I plot the histogram of that and normalize it, it should look like the PDF. So can I draw that? When you can draw those samples, those are known as realization. So that means when you draw those samples, so think I have a Gaussian distribution. I am drawing samples from the Gaussian distribution. What will that sample follow? It should follow the Gaussian distribution. So when you draw something like that, you will use this notation. Where is that notation? Yeah, the bottom one. X is a sample drawn from Gaussian distribution with mean mu and covariance or variance sigma square. So one is you are drawing sample, I will call it realization. The other is you know the sample, now you want to evaluate it. So both are same eventually, but one is going from A to B or B to A.
So essentially, the input and the drawn sample, they are same.
Input can be X, but input is not one X. Input can be a number of X. Because X is a random variable. So this X, I said, takes value from anything from minus infinite to infinite. So what is the value of X we are talking about? In that whole, it is in the whole universe can be the value of X, right? When you draw sample, then X has a specific value. If you draw it again, it will become something else, but one draw will give you one value. Now for that value, what is the value of PDF? How will you find it out? You will take that X and put it here. So obviously that is again the function here. Okay.
When we take samples X and Y, and so they are just observations of the PDF.
Experiment.
So what do we mean when we later go on to say that Y is G of X? Like how can a randomly taken sample be a function of another random?
It is possible, simple. Suppose I am measuring simple example. Suppose height and weight of the students. Height is random, weight is the function of height. Weight is also random.
Yeah, but when you are taking the
Sample, your height and your weight will be related by some function.
height has one distribution, weight has one distribution.
Correct.
If I take a sample from height,
Let's say one
and
sample.
I get the height of student 1, 2, 3, and from weight I get the sample of student 4, 5, 6, and how will I?
No, you have to realize that. So what is the sample? What the sample means? One sample will mean your height and your weight. That is one sample.
So we are given this that the samples that we draw are from the same observation.
Obviously, there is a function. Your height and weight is related by a function. So we are going in the opposite direction. Think about it. There is a relation between height and weight. If height is more, weight is more, so we can find some relation. Now I am saying height is random. So you are going in the opposite direction. I am not saying height is random, then I am drawing sample, what is the relation? I am saying height and weight has relation. Now height is random, therefore weight is also random. But how are this randomness related? How are the PDF related?
So even though if we have some sample and then we take some function, for example square, so the sample that we obtain is also a random sample.
Obviously,
So
definitely. But what he is saying is if I draw separately from two distributions,
then also
they are related, but which is related to what? So for example, let's say I draw from X, I get 1, 2, 3. I draw from Y, I get, I might not, I get some 8, let's say 4, 18, 16 and 32. Now there is no one-on-one relation because these samples are random, these are random. But if you draw one sample and do the transformation, they are still samples from their other distribution. So that sequence is to be followed. So that's what the doubt is. He is saying that I am drawing separately from two. How can I relate? I cannot. I will draw from one, do the transformation. Whatever I get is now also sample from some other distribution. So the sequence is to be followed. If you draw randomly, you cannot, until and unless you draw infinite number. And then probably you will find some link in the whole thing. Okay. So the idea is, okay. So the idea is that here, there are two variables. You know the relation between the two variables. And you know one PDF, what is the PDF of others? Right? Think of it in this manner, because that is the real problem. Okay. Any other question? Okay. So if there is no other question, let us move on. And now this is the end of the review part. And now let us start with Bayesian inference. So this is the real machine learning stuff that is going to start in a short while, not today, but yeah. The name Bayesian comes from Bayes' law, Bayes, quite clearly. And so what is the main formula you are expecting here to see? The Bayes rule. That has to be the main formula that you expect to see. If the name has been derived. If it is Newtonian mechanics, you expect to see the Newton's law. If it is Eulerian, you expect to see Euler's axiom. So, like that, if it is Bayesian inference, you expect to see the Bayes law. Okay? So, basically, the Bayes law, along with that, the sum rule and the product rule, because Bayes law is based on that. So, what is the Bayes law we will be using? So, probability of theta given d is equal to probability of theta d given theta by probability of d. Okay. This is the form that we will be using, but before I start discussing this form, let us discuss about the Bayesian way of looking into things. So, as I said, remember that probability and statistics is a way of thinking. So is Bayesian statistics. And the philosophy of Bayesian statistics is that whatever is unknown is random. Because remember last class I said that something is random because I have limited knowledge. So, randomness stems from my limitations that I do not have complete knowledge. So, in Bayesian way of thinking we reverse it, and it is whatever is unknown is random. And whatever is random, we will model it as a PDF or PMF depending on discrete or continuous. So, that is the Bayesian way of thinking, that is the main philosophy we will be following. Okay. The main philosophy is whatever is unknown is to be considered random. Okay. That is the main philosophy. Now, come back to the Bayes rule and let us see. Let me write it down once again. So, the rule is, or Bayes law actually, is equal to probability of theta, probability of d given theta, probability of d. Okay. So, this is the Bayes rule. Let us try to dissect it and try to understand what this rule is telling us. Okay. So, we have two things here apart from probability. One is theta, one is d. Theta stands for parameters or whatever is unknown. Okay. So, theta stands for parameter or whatever is unknown. In our case, it will always be parameter. So, theta is the parameter that we want to infer. Okay. So, it is the parameter that we want to infer. What is d? Calligraphic d always is data set. So, you want to infer some parameter based on certain data. Okay. So, d is my data. We will take one example soon, and that will, with that I will explain this again. Okay. So, d is data. Data means measurements, observations, outcome. So, I have performed some experiments and observed something, that is my data. Okay. So, let us take one example and try to understand what this will look, and let us take the simplest possible example, tossing a coin. So, I have been given a coin. Now, with that coin, I do not know whether that coin is biased or unbiased, I do not know anything about that coin. And my objective is to find out the probability of head, because if I can find out probability of head, I can find out probability of tail. Clear? So, what will I do? I will perform experiment, right? I will toss the coin again and again and see what I am getting. Suppose I perform the experiment, I do not know, n number of times. So, I will have some data which is head, tail, tail, head, I do not know what we will get, but yeah. So, we have a coin and we want to compute probability of head, right. So, we perform n experiments, we perform n experiments, okay. And the output of the experiments, let us say, is head, tail, 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 head. I cannot write n, so head, tail, tail, okay. Something like that I have got. So, this becomes my data, and what I want to find out? Probability of head. Let us say probability of head is equal to mu, okay. So, mu is my theta, that is the parameter I want to infer. So, the Bayesian way of thing is that I will try to find out probability of mu given d, where mu is my theta, d is my data, and there are other things, okay. Now, how to find it? We will come to that later. I have not even explained the each terms of the Bayesian Bayes law in this context, but this is the thing, right. This example is clear, and can you relate it with theta and d now? What theta and d is? Okay. Theta is my probability of head, and now here is the thing, probability of head. So, probability itself is now random, because probability of head I want to find out, and I am trying to find probability of head given theta, because probability of mu is probability of head. So, it is like finding out probability of head given some measurements, okay. So, the probability can now vary, at least if I can compute this. Questions? Okay. So, now if that is clear, now let us go back to this now. So, what is probability of theta given d? This is a name, this is known as posterior distribution, okay. And this is basically your, if you think carefully, this is your or our belief about theta given the data set. Given that I have made some observations from the data, what is now my belief about theta, right. So, this is belief about theta given d, and we call it posterior because it is the your belief after, that is post, you have observed the data, that is why the term posterior, clear. The other term we have on the right hand side is probability of theta. This is the prior distribution, because this is your belief about theta before you have observed any data, and your belief can be okay. In my whole school days, I have always worked with unbiased coin, so the coin is unbiased, that is your belief even before you have performed any experiment. If you have such a belief, that becomes your prior, okay. So, this is the prior distribution. Belief before any observations. Okay. Now comes the third term, which is the second term on the right hand side at the numerator, which was probability of d given theta. So, this is probability of d given theta. This is known as data likelihood. Why such a name? First of all, you are finding probability of data, so the term data makes sense, and then likelihood, because how likely you are to observe the data given some theta. Likely, probable, these are close by term. So, it is basically telling you how likely you are to observe data given theta, and that is why we call it data likelihood. likelihood of the data. And this likelihood of the data depends on the experiment you are performing, the data generation process, and I will illustrate it with an example soon. Okay. So, this you have to remember depends on data generation process or the experiment you can imagine. Okay. So, P of theta is your prior belief about the parameter and it is just your prior. P of data given theta is bringing in information from the data now. Okay. And by combining this, you are trying to update your belief. And by updating your belief, you are getting the posterior belief, posterior distribution. Obviously, there is one more term which is mostly not used, but that is known as the evidence. So, the last term that is there in the denominator, probability of D, this is the evidence. This is important because you will never have infinite data, right? You will always have finite data. Remember, if your data changes, then your everything changes, calculations, right? Because it is a function of data. So, this is like in the all possible data, the samples you have, what is the probability of that? And this is intractable, you cannot compute it easily, and that is why we do not use it in most cases, apart from some cases where this is tractable. So, this is mostly intractable. So, it is very difficult to compute, almost impossible in most cases. Okay. Clear? So, now based on the discussion over the last 5 minutes or so, what are the things that you need for this course? Let us try to understand. First is prior, you need a prior. So, if I have some belief how to encode into a prior, for example, if I say that I have prior information that my parameters cannot be negative, possible? In that case, what prior should I take? Simple, actually log normal. If I say I know that a priori that okay, my parameter has certain properties it should satisfy, can I have a prior that satisfies those properties? Let us say translation invariance, rotational invariance, can you come up with some prior that will satisfy those properties? So, basically given your prior knowledge how to find a suitable prior distribution. So, that is known as prior modeling. That is the first thing you will need to learn, and unfortunately that is not very well developed. That is a huge research area. Many people are working on that research area, how to develop prior based on some knowledge, how to encode prior based on knowledge. So, we will be talking about the established literature in that area, but that will be very sparse and you might feel cheated that okay, where am I encoding my prior belief? In many cases you will feel like that. You will realize that okay, that we are using for maybe computational convenience to get analytical solution, but where is my prior belief here? Believe me, it is possible, but that is work in progress, and we are not going to talk about such priors. We will talk about translation invariance and non-negative and all those things, but not about let us say some equation is there, I want a prior that satisfies that equation, those things we will not talk about. But nonetheless, the first topic is prior modeling, and we will spend some amount of time on prior modeling, 4 or 5 lectures let us say. So, the first thing you will learn in this course is prior modeling, given how to model prior, what are some of the popular priors, what are the property, what if I do not have any information, then there is non-informative prior. What if I want to make my calculations analytical, then there is conjugate prior. So, all of those things are there, we will talk about that. The second one is likelihood, and I said that likelihood depends on the data generation process, on the problem you are solving, but it is important to understand likelihood. So, we will talk about that little bit, but that is very problem specific. So, it is very difficult to talk about it in a generic manner, we have to talk about it with some examples, and one such example I will take soon today. The third one is to computing the posterior, and this is the main thing we will be talking about. So, basically we will assume that we know some prior, we know the data generation process, we know the likelihood, but given these two things, how can I compute the posterior? Given that I have already told that P of D is intractable, so I cannot get it in closed form. So that is the whole computation part. So, and we will spend significant time on this part in this course. So we will talk about sampling based method, we will talk about analytical solution, we will talk about approximate methods and all of these things for computing the posterior. Okay. So that is, and these three things combined is 70 to 80% of the course. So this course is mostly about these three things. Okay. So you will see repeatedly I will be referring to these things again and again on like every lecture. Okay. So these are the main things we will be talking about. Obviously there can be a model selection problem that I might also talk about. So one thing and the last thing for today is the likelihood, and I said that likelihood or data likelihood depends on the data generation process. So let us take one example, the same example, this one, and try to find out what is the likelihood. Okay. So we revisit the coin tossing example, right? And my data in that case was, I forgot, but let us say I will write something. And I have n such measurements, right? What is my theta here? Theta is equal to mu.
N is just a number.
N is just a number of times I have performed the experiments. Okay. So theta is my mu, right? So what is the likelihood now? Probability of data given mu, data given theta, that is my likelihood that I need to compute. So the idea is, what is probability of data given theta, and theta is mu. Now what is data here? These experiments. First question, whether I get a tail or head in the first experiment, is it influencing what will I get in my next experiment? No. Independent. So I can easily write them as product, the product law with independence, right? So this will be equal to product of I equal to 1 to n probability of xi given theta. Xi is the outcome of the first experiment, ith experiment. So what will be x1 equal to? What will be the value of x1? No, not probability, x1. x1, what is x1? Outcome. What is the outcome? x1? But for me it will be 0. Random variable. So tail will be 0, head will be 1. Don't forget that. I am writing it like that, but tail is 0, head is 1. So my x1 is equal to 0. x2 is equal to 1, x3 is 1, x4 is 0, and xn minus 1 is 0, xn is 0, and other things I do not know. Clear? Now, what you were saying, it is a coin tossing example, right? One time I am tossing a coin. What is the probability of getting x given theta? 1 by 2 if this is unbiased. It is not, I do not know theta. So it is the PMF, right? So what is the probability there? What is probability of xi given theta? If I toss a coin, if I get a head, the probability is mu. If I get a tail, the probability is 1 minus mu. So the mu is theta. So in that sense, and then so my PMF for this is the Bernoulli distribution. Coin tossing is Bernoulli distribution, which is mu to the power x multiplied by 1 minus mu to the power 1 minus x. So now given that xi will be either equal to 0 or 1, right, binary value. It follows Bernoulli distribution, because Bernoulli distribution is for when any scenario where you have a success or failure case, tossing a coin, head or tail. So, anywhere where there is a success or failure and you are doing it each time, that is a Bernoulli distribution. If this is not clear, see the video, there is a whole thing on Bernoulli distribution last time I did. So, see that, okay. But Bernoulli, so it follows Bernoulli distribution. So, probability of xi given theta, where theta is equal to mu, will be equal to mu to the power xi and 1 minus mu to the power 1 minus xi, okay. And not like this, I should be above, I should be in the superscript, right. And you can check this how? Suppose you get a head, then what is the value of xi? Then what is the value of this? Mu, mu to the power 1, 1 minus mu to the power 0. So, it will give you mu. What is mu? Probability of head. If you get a tail, then it will be equal to 1 minus mu, which is the probability of tail. So, the property satisfies. If you do a summation, you will get 1. Do a summation over all values of x, you will get 1. So, I got my likelihood, not this, but my likelihood is therefore probability of given theta is equal to product I equal to 1 to n mu of x I 1 minus mu times 1 minus x I, right. Now, this likelihood is Bernoulli because it is a coin tossing example. Now, suppose instead of coin tossing, this is a taking a card out of a deck, then what will this look like? Will this be the same? Why? Because this distribution will change. In that case, it will become multinovely. Okay? So, that is why I said multinovely is also important. If you throw a dice, even that is multinovely. So, this probability will change depending on the problem you are solving, depending on the experiment. Since it is a coin tossing example, this is turning out to be of this form. If it is not a coin tossing example, it will be of a different form. So, the form of the likelihood changes with the experiment or the problem you are solving. So, the form changes with change in experiment type. Example is for coin tossing, we are getting Bernoulli, product of Bernoulli. So, let us call it Bernoulli, but for dice throwing, it will become multinovely. Okay. Okay. So, the form changes with change in experiment type. Clear? Okay. Okay. So, now we need to talk about methods now, right. So, primarily we will be using the Bayesian, that is what the course is about, probabilistic machine learning. So, Bayesian, but even if we do not, if sometime people do not want to use Bayesian, the reason is that is very expensive. So, what are the different options we have? So, the options are, so different ways of computing theta. The first one is known as maximum likelihood estimation or MLE. Here the idea is theta star is equal to, you will maximize probability of D given theta. Okay. So, let us discuss this equation for some time. Okay. So, what is probability of D given theta? The likelihood. Okay. So, why should we maximize it and take theta? So that the probability increases, but why do we like to increase the probability?
Because we want that the sample which we have observed, we want to claim that it is coming from.
We want to maximize the chance
Yes.
probability, which means we want the theta that best explains the data.
Yes.
We want, for if the probability is more, what does it mean? The theta that will give the maximum probability, that is best explaining the data. That is why the probability is more. I always give this small example. So, suppose I am one of us, like, or we, let us say, are travelling from here to Kerala for a trip. Okay. Now, we can travel by flight, we can travel by train, we can travel by bus. Okay. And there is someone there to receive us. So, now before we leave, we call them, we call that person, or someone from us call that person and tells that, okay, we are leaving now. Okay. And then that person see that we reach there 5 hours after I called. Okay. So, what is the data here for that person? The data for that person is that it took me 5 hours, took us 5 hours to travel from Delhi to Kerala, right. Now, how will the mind work? What will it think? What was the mode of my transportation? Definitely flight. Why? Because in his mind he is doing the calculation that given that he has come by flight, it is taking 5 hours. If he was coming by train, it would not have been 5 hours. So, that probability of explaining the data, which is travel time, is equal to 5 hours. The data that travel time is equal to 5 hours is best explained by the mode of transportation is equal to flight. So, the probability of data, which is travel time 5 hours, given mode of transportation is equal to flight, will be maximum. Probability of reaching in 5 hours given train is almost 0, and the other thing is also 0 plus, right. So, this is how our mind works, right, and this is how this thing works. Now, will it be 1? No, it will not be 1, because it is possible that I called him after I was in train, I called him 5 hours before I was supposed to reach. So, there are all these extreme scenarios. So, it will never be 1, but it will be more probable. So, the scenario will be most probable, and that is why we will maximize it, and that is why you call it maximum likelihood estimation. Clear the concept? So, we will not solve maximum likelihood estimation today, but we will solve this problem using MLE in our next lecture. But I will want to talk about the Bayesian way also, that I did not say. What is the mentality here? See this one. So, we have some prior, we have some likelihood, and we have some posterior. Think about this class, right. So, some of you were repeating in the sense that you have done my other courses, but some of you are new. So, before you registered for the course, you saw the course content and you thought, okay, this is a teacher or someone who is going to teach, I do not know anything about it. Maybe you talked with your friends who have taken some course from me, and that became your prior knowledge about me, prior belief about me, right. That is your P of theta, your prior belief before you have interacted with me, right. Then you enrolled for the course, started coming, maybe you have done for 3 classes. So, now still your data is very less. So, your belief now is a combination of these 3 classes that you have interacted and your prior belief. But probably towards the end of this course, you will be dominated by your interaction D only. By that time, your prior might change or it might get reinforced more, but it will be governed mostly by the data. So, as a human, whenever we are taking any decision, it is based on our prior belief our prior notion, preconceived notion, whatever you think about it, and the data that we are collecting through our ears, eyes, nose, skin, and the 5 senses. And based on that, our belief system is getting updated, right? So that is again the Bayesian way. So Bayesian way is actually also how mind thinks. Okay. And the other thing is the MLE way is how we take decisions. If we have to give a point estimate, this will not give a point estimate. MLE will give a point estimate, and that is a good and a bad thing. Okay. So, first of all, MLE gives point estimate, right? You are getting a value of theta, you are not getting a distribution over theta, right? The second thing is MLE does not consider prior belief. This definitely is a bad thing. Okay. So, you might want something where the prior belief is there, but it is still a point estimate, and that is known as the MAP, maximum a posteriori estimate, which is an improvement over MLE. So, maximum a posteriori estimate, and here what you are doing is theta star, you are still getting a point estimate, you are maximizing a probability, but you are maximizing the theta given d instead of d given theta. So, theta given d is proportional to prior times likelihood. So, your prior is now coming into picture. So, this is equal to argmax probability of theta, probability of d given theta. The denominator does not have theta, so I can remove it. So, if you do that, this is known as the maximum a posteriori estimate, because what you are doing, think about it. What is theta given d? Theta given d is your posterior distribution. What is maximum of that? The mode. Maximum of a distribution is the maximum frequency, that is the mode. So, that means you are trying to find out the mode of your posterior distribution, because that is the most frequent one, and you are saying, okay, I will take this value because this is the most frequent one in the posterior. So, that is the point estimate, right. And then the third one is obviously Bayesian, that we have already discussed. So, I will stop here. Next class we will start with the MLE, we will solve the problem of the mu, finding out mu with MLE, and then we will continue from there. Okay. So, we will see you on Wednesday. The venue is 4LT2, but it is not yet confirmed, so I will write an email once I get the confirmation from them from 3 p.m. for the practical, 4LT2. Okay. So, I will write an email. Okay. Thank you.